Hello, my dear students, and welcome to a final recording for this analog course under the name of Electronic 3 module. Today, we are going to terminate our oscillating chapters with discussing more, let me say, relatively sophisticated design with respect to the principal design we have already observed in the previous maybe two recordings. So let me go directly to the PowerPoint slides I have. And let's start sharing the presentation slides, and let's start also open the pointer. Okay, so in the previous lectures, we have demonstrated the main idea of an oscillator constructing of an amplifier and a frequency selection network, or what's called a beta network, where we reach a conclusion that in order to reach an oscillating frequency, this oscillating frequency is a frequency at which the condition A beta is equals to 1, considering that generally speaking, the A network or the amplifier can be an S-dependent or in terms of J omega, and so of course, the beta selection network is also an S-dependent or a J omega network. So we are searching for this omega node at which we can reach the condition of A beta equals to 1. So we demonstrated a lot of circuits. We start with this fundamental circuit where we reach two main constraints. The first is that physically it is not applicable to reach a typical A beta equals to 1 due to this R1 over R2, because in order to reach an A beta equals 1, you have to set R1 over R2 equals to 0, which is practically impossible. And also we find another important issue related to the limitation, in the oscillation amplitude. So generally in this schematic, this oscillation amplitude is going to expand till it is going to saturate by the terminals or by the DC limits of the operational amplifier, typically VCC and negative VCC. So we don't have any sort of control to this amplitude. So in order to solve these two issues, we have demonstrated in the previous chapter, or maybe in the previous recording, we have demonstrated what we can call the nonlinear amplitude control circuit, where you can control the amplitude of your amplifier by inserting these two new diodes and these 4 series resistance. So you can control the amplitude at some certain point. When this point or this point reach negative 0.7, 0.7, your amplitude will be controlled by this combination. As we already discussed, maybe you can return back to the previous recording to know more about that. And also we introduced another circuit to act as an RC, or as a frequency selection network. We're introducing this RT network, where in this RC you can reach a condition that you just need R2 over R1 to be equals to 2 in order to get a typical A beta network, which is of course applicable. And we combine all these ideas in one schematic, and we studied, maybe this was the final slide in our previous recording, when we study this combined architecture, including our A beta network, including our beta network, this RC network, our standard non-inverting amplifier, and this amplitude controlling network. What we are going to do now is that we are going to explore more architectures in the same trend, in the same direction, toward implementing an oscillator. So this one of the architectures. Actually, the main idea here, this is a very general idea in electronics generally, that you can never find one type of circuit by a single architecture. For any electronic circuit, you will find a lot of alternatives, and definitely there is a set of trade-off parameters that can evaluate these different alternatives. So you can find the pros and cons of these alternatives. Maybe we will not have enough time during this course to investigate the pros and cons of all of these, but the general idea here is that to explore that we have alternatives, and the same function can be implemented by different architectures. So this was one of the first architectures to do an oscillator, but again, we can use this to do an oscillator. So generally speaking, when you find something like that in your exam paper, just start to think in a very organized manner. So first of all, we know that an operation, an oscillator is typically a combination of an amplifier with a positive feedback of a frequency selection network. So your first step always is to distinguish between your amplifier network and your frequency selection network. So simply speaking, I will going to use my annotation now. Okay, so yes, that's amazing. So this is again our frequency. Yeah, it's not appropriate. Let's make it in a different way. Yeah, this is our frequency selection network. This is typically the same as our previous architecture. This typical RC circuit. This is our frequency selection network, and we have now an amplifier. So this big circuit is our amplifier. You can see that still we have these two diodes that should somehow control the amplitude, and we will discuss together now how we are going to control the amplitude by this configuration. But this is generally the circuit. So what you are going to do, my dear students, is you are going to investigate each of these circuits independently, and then you can get the A network, the beta network, and then reach the condition of A beta condition. So let's start doing that. And as usual, let me start now. We're referring back to our whiteboard. So yeah, I just need to switch my camera to the whiteboard. And let's stop sharing for a while and go to the whiteboard. Okay, so our beta selection network is typically the same as our previous example, which is an RC network. So let's do it again just for a version. So we have here a resistance, a capacitor, a resistance, a capacitor. Both have the same value, so R and R and C and C. If you remember, I already investigated with you this circuit before, and I think I can told you directly about the final. So the final configuration, I think it was that V output over V input equals to 1 over 1 plus J times omega RC minus 1 over omega RC. So this was the final resultant for this network. I think we already investigated in details when we did this circuit in the previous recording. So you can refer to the previous recording for more information about that. It was very simple. Let me remind you directly that we make a combination of these two parallel components. So the admittance of this parallel component, I call it, if you remember, Y2 equals to 1 over R2 plus SC. So simply the Z, or the impedance, is the reciprocal. So it's 1 over 1 R2 plus SC. Or it's R, not R2, it's just R. So 1 over R plus SC. So this is Z2. And simply Z1 is that series combination of these R and C. So Z1 is simply R plus 1 over SC. So you have Z1 R plus 1 over SC, and you have Z2 equals 1 over R plus SC. And as you can see that the output voltage here, this node, is a potential divider of these two networks. So simply speaking, you can say that the output equals Z2 over Z2 plus Z1, and this will result with this network or this circuit. And as we discussed earlier in the previous recording, that in order to get rid of this imaginary part, so what you are going to do is simply is that you can say that this term should cancel this term. So omega RC should equals 1 over omega RC, or in other words, omega it should be equal 1 over root RC. So having the same frequency selection network with an amplification network, which is frequency independent, as in our case, that simply means that you are not going to change the oscillating frequency, because typically, as you can see here, the oscillating frequency is a frequency dependent parameter, depend on the omegas, which generally appear whenever you have a capacitive or an inductive. Of course, we don't have inductors here, so it appears whenever you have an capacitive part. So by having the same beta network, you can have the same oscillating frequency, but take care, this is considering that your amplification network is a frequency independent, as in this case. So this is typically what we have in the beta network. So let's go to the other side of the story, which is the amplification network. But please take care. I will return for a while to my presentation slides to show you something important. So here, please take care that we have here, I'm sorry, yeah. Here we have this potentiometer or variable resistance. So when you see this in your exam paper, please don't be shocked. This simply means that you have here a splitted resistance with a factor, it's called P. So between the ground and this point, we have, for example, 50K multiplied by B. And between this node and this node, we have another 50K multiplied by 1 minus B, so that B is the tuning parameter varying from 0 to 1 to control the value of these two variable resistors. So let's do it in a circuit way. I will try to plot this circuit somehow to make it easy for you to understand. So it's simply like that. We have, this is our operational amplifier, this is an inverting and this is a non-inverting, and the input is connected here. So this is the input. And for the negative terminal here, we have a resistance on the ground. I'm going just to check that, yes, you can see what I'm drawing. This is perfect. So the value here is 50K times P. Now we have this terminal with another resistance, which is the remaining part of the potentiometer, which is 50K times 1 minus P. And herein we have our distinguishing point. So here at this point, you have 3 branches. You have a reverse diode, a resistance, which is 10K, and a forward diode. So this is a combination. And then we have the feedback network. And this is the, yeah. Here, I just need you to recognize a very important point here. So again, I'm sorry, but I need to return back to my presentation slides. Here, what is important, my dear student, is that we have a very tricky point in the design here. The tricky point is simply that your output for the oscillator is not the same node as your positive feedback point. Let me describe this. So herein, for example, this is the output for the oscillator, which represents the same as the point giving this positive feedback. So this node is a common node. So it's the output for the oscillator. And also this is the point carrying the positive feedback to the beta network. So if we just recognize that this is our beta network, the input of the beta network is this terminal, which is typically the same as the output. Again, as you can see, it's a central node here. However, here, the input for the beta network, which is conceptually the output of our amplifier, is this node. However, the output of the oscillator itself is this node. So it seems like you have 2 outputs. You have an output for the amplifier network to feed the beta network, which is this terminal. I will call it VOA or V output for the amplifier. And we have another general output, which is this terminal, representing the output going from the oscillator itself, the general output of our network. So just take care of that, because this should be confusing if you didn't recognize it from the first impression. Okay, that's great. So we have to consider this. So as I just told you, my dear students, what I'm going to do is, let me return back to the point. So I will call this point V output A to represent the voltage outputted from the amplifier to be inputted to the beta network. And this point, I will call it V out. And please don't confuse, this is the general output. Of course, this is here the trick. When you consider to determine this A of S, here your concern should be the relation between input and output of the amplifier. So you are not going to include this, or it's not your task now to discuss this point. But you have to consider the relation between these 2 points, because simply these are the points constructing the amplifier. So let's do this, or let's see how this circuit is going to control the input, or the control to limit the input, because actually this is the task of this network, to control the input. So I'm going to repeat the same procedure as we did in the previous lecture. So as you can see, this is a typical non-inverting amplifier. So when we consider that, for example, that this V input is very small positive value, let's say that this is 0.0001, very small input value. Please don't forget that this input is generally some sort of a sinusoidal signal fluctuating between positive and negative. So for a very small input, what will happen, my dear students? Let's see what will happen. So if this point is very, very small, as you know, this point and this point are equal. So this is again the input, which is positive 0.0001, this very small value. And this is ground. And this should be some sort of an amplified version. So let's assume, as we did in the previous example, that we amplify by 10. So this 0.001 will be 0.01. So it's a greater value, a positive greater value. Herein, we should assume a current flow in this direction, simply because this is a positive value, this is the positive value, this is the ground, this value is greater than this value, so generally current should flow in this direction. Okay, however, so as far as the current is flowing in this direction, that means typically that this diode is off, that this diode is a reverse bias, so I will not consider this diode in this case. But what about this diode? To turn this diode on, that means that the voltage drop on this diode, let's call it D1, for example. So the voltage drop in this D1 should be greater than 0.7. I mean, this voltage should be greater than this voltage by 0.7. If this happens, this will be a forward bias. Otherwise, it's still reverse. So as far as this voltage is 0.001 and this voltage is 0.01, definitely the voltage here drop is very, very small, so it's still off. That means that again, D1 is not here. So basically, what you can going to see here is that you have this 10K connected in series with 50 times 1 minus B. And this here, consider your feedback resistance. And you have another 50 times P in this connection. As you basically know, the gain here, the A gain, will be 1 plus the feedback resistance, which is 50 times 1 minus B plus 10 over 50 over 50 times B. So this is typically the gain when you make this ratio or when you make this ratio is equal, when these two diodes are reverse biased. So this is typically will be the gain. Okay, so the question is, as far as the input is positive, and definitely the output is still positive because this is a non-inverting amplifier, so the current is flowing in this direction. So in all the positive cycle, we should consider D2 as a reverse bias. We should totally ignore D2 in the positive half cycle of the inputs, which is this one. Okay, so the question is, there is a point somewhere where this D1 will turn it to be on. It's the point at which the voltage drop here becomes 0.7. So as the input voltage increase, this point is typically the input. So it will going to increase, and this will increase in a more rapid way because this is the amplified version of this point. So when the difference between these 2 points, V output and V output A and V output, reach 0.7, this D1 will going to be turned on, making these diodes short circuit. When these diodes become a short circuit, that means typically you are short circuiting the 10K, and this results with another gain. I will call it A saturation or the saturation gain, giving that 1 plus 50, 1 minus B over P, over 50P, of course. So 50 will be canceled with 50, giving that 1 plus 1 minus B over B. So here, please return back to our previous recording regarding the control of the saturation gain. So typically you can manage whatever you want. If, theoretically speaking, if you are intended to make this saturation gain typically equals to 1, you can do it very easily by putting this P very, very high and this 1 minus B very, very low, or simply by turning this P to be 1. So 1 minus B is equals to 0, and then you will get typically 1 gain. But as we mentioned in the previous lecture, that usually we intend to make this saturation gain slightly greater than 1 to compensate the resistive losses in the beta network, if you remember. So that means that you will make beta approaching 1, but not typically B, so not beta. You will make BP equals tends to 1, not typically equal 1, so that you can make a gain which is slightly greater than 1, typically as a previous circuit. And of course, you can do the same process in the negative half cycle using this D2 diode. So simply, as you can see, we did the same approach of amplitude control, but maybe using a more simple circuit with respect to the previous circuit we insert. In the previous circuit, we have 2 diodes again, but with a branch of a 4 resistance. Here, we just have 1 resistance and 2 diodes and a potential or a variable resistance, and we did the task of an amplitude control. So this is, as I mentioned, we are doing still the same task, but with using different architecture, different topology. So this is another implementation of having an oscillator for that. Okay, that's great. Let's see another approach for oscillators as well. So this is a more complicated approach. So as you can see here, my dear students, we have the same performance of an oscillator, but this is actually a relatively more tricky circuit because we have here a very straightforward constant amplifier. So this is typically our amplifier. Let's do the annotation and let's open here. Let's open here. Oh, yeah. So this is typically our amplifier. Here, as you can see, our amplifier is directly straightforward. It's 1 plus 2R over 2R, or 1 plus 1, which is a 2. So it's a double gain amplifier. Very straightforward. But our beta network actually is not straightforward, as you can see, my dear students. So I will again try to, here. So our beta network, as you can see, we have here a resistance, we have a capacitor here, and we have this branch, which is very, very, very close to the
amplitude control network. So we have a similar amplitude control network. And by the way, this is very logic because we don't have any type of amplitude control here, as you can see. So you somehow integrate the amplitude control with the beta network, because here you have a capacitor which will perform some sort of a filtering task, and you have a combined beta network here, or sorry, a combined amplitude control here. So this is some sort of intrinsic circuit. So your beta input will be this point. You have a resistance and a capacitor. By the way, if you neglect this controlling circuit, it will result with a very standard and a typical integrator with a capacitor in the feedback and a resistance. This is very straightforward. But as you can see here, this straightforward network will try to change a bit by the condition of these bands. We will consider this. And then you have another type of a filter considering a 2R and a C resistance. So this is an RC filter. So let's make it with different colors just to make everything clear for you. So we have here, I'm sorry, this is not, what should I plot? So here. And we have, let's change the color for a new color. And let's do it here. And finally, okay, so I'm sorry for all these too much squares or rectangles, but it is the simplest way to make it. So this purple box represents a very standard amplifier. It's a double gain amplifier. We don't have to think about it. It's a gain equals to 2. Let's keep it. So then we have a double stage beta network. What is new here? We have a lot of new tricks in this design, but one of these new tricks is that we have a double filtering stages. In the first filtering stage, we have a very standard integrator, RC integrator, but this RC integrator is associated with this orange, or yellow, it should be orange maybe. So orange rectangle here. So let's start to discuss. We know, we of course know the integrator. It's very easy. This point is ground, so this is a virtual ground. The current flowing in this resistance is typically the same as the current flowing in the capacitor. So I believe that you can do it very easy in a very easy manner. This is not a challenge. But what may be a challenge is this network. So how this network will perform, it's very easy. So when the inputs, when the difference between these nodes, which previously we call it A and B, if you remember from the previous recording. So when the difference between these two nodes, for example, is smaller than 0.7, and when the difference between these two nodes is smaller than, or if it's 0.7, then this is a short circuit. If it's open, it's not 0.7, it's an open circuit. So typically speaking, for a very, very, very small inputs, either in the negative half cycle or in the positive half cycle, you will find that this two diodes will be reverse biased, and then there is no current flowing here, and typically you can totally ignore the circuit. But if let's consider the case when this D1 is a short circuit. When this D1 is a short circuit, that means that you add a resistance called R2 parallel to this capacitor C. So you have R2 and C here, and that's slightly change the performance or the gain of your amplifier. You may check it by circuits. Just put this R2 parallel to this capacitance C and see the effect or the variation. So just to describe it in the circuit. So in the very small amplitude, you will have something like that. This is a negative, this is a positive, this is ground, this is the input, and there is a capacitor here. So this is a typical integrator. But whenever the amplitude starts to increase a bit, you will find a resistance here in parallel. So what you are going to solve simply, first you are going to solve without this resistance, and then you are going to solve with the resistance. Let's see. So if we don't have this resistance, so we have R and C. And simply, as I just said, the current flowing here is typically equal to the current flowing here. So what you can say that V input over R equals negative V output over 1 over SC. Or V output equal negative SC over R times V input. Or V output over V input equal S. I think no, this is not correct. I'm sorry. So it's here. So it will be the output equals negative 1 over SRC times the input, or V output over V input equals 1 over SRC. This is typically what we previously did. This is typically the integrator. But what if we add this resistance? What if we have this R2 resistance here in parallel to the capacitor? So it should be something like that. V input over R, again, equals the output over negative V output over 1 over SC, negative V output over R2. So V input over R equals negative V output SC, negative V output over R2. Or it should be negative V output over times SC minus 1 over R2. Oh, sorry, plus, this is plus 1 over R2. So you can pick this here. So you get V output over V inputs equals negative 1 over SC plus 1 over R2 times R. Or in other words, you can say 1 over SRC plus R over R2. You can multiply by R2 in the numerator and denominator, so you can get R2 over R2C plus R. So what is the difference between this term and this term? So to explore the difference is very easy. Let's express what we can call the DC gain. Here, the DC gain theoretically is equals to infinity. It's very high because a DC gain means that omega equals 0, which means that S equals 0 because typically S is J omega. So if you put S here equals to 0, that means this term is equals to infinity. However, if you have here S equals 0, you will get a term R2 over R1. And if you put R2 just slightly greater than R1, which means that you get a slightly greater gain. So you can't control the gain. So here, the gain is limited, but here, the gain is infinite. So adding this small resistance in parallel to the capacitor control the gain. In the beginning of the cycle, you see a very high gain. Once the amplitude starts to increase and the dials turn to be on, a resistance is going to be added to your network to limit the gain to be equals to R2 over R, and you can control this R2 over R. So this is, again, now you understand the function of this circuit or this part. So now we understand this and we understand this. After that, you will face another filtering stage with 2 RCs. This is a very standard filter. I think this is a very standard low-pass filter, another low-pass filter here. But what I will keep you to think about is typically, my dear students, this resistance. This is one of the very tricky resistance in the design of oscillators, where we connect these two terminals. Please take care that this terminal is represent the input terminal of your beta network, and this terminal represents the output terminal of your beta network. So it looks like you are connecting the output and the input. That's why we call it RF. This may be a point to think about in the end of this module is what is the role of this RF? Why we insert this RF in this place? So far, we can understand the general concept. We have here an amplifier. We have here a beta network, a filtering beta network with an amplitude control. And we have another second stage of an amplifier. But what is this point? How we can consider this point? And you can refer here to the reference to consider this schematic, where we schematic this 2R, C, and RF with a negative sign, or what's called, we call it the equivalent negative resistance. This is a very tricky part of the circuit, which may be kept for you to think about. I will welcome your answers, proposals, suggestions in that to explore the importance of this negative or the importance of this feedback resistance. So this is the determination for our module, where we consider three main chapters related to the analog electronic design. First, with the alpha stage power amplifiers. Second was different types of active filters, considering cascaded, SAPs, and tuned amplifiers. And finally, dealing with oscillators. I hope that you enjoyed the course, and of course, I totally welcome your questions whenever you have through my email or any other communication platform. Thank you very much for your concentration. Maybe see you in next lectures, inshallah, or next modules, inshallah. Thank you very much.